video for chapter 27, and I will talk here about motion of a charged particle in a magnetic field. Then I will say when I will have an object that has a charge and it is entering a region where we have a magnetic field, and then I will say here we are going to have a force acting on that particle. That force, it is the magnetic force, and it is always perpendicular to the velocity of the object. Therefore, this force is going to be a centripetal force, and since it is perpendicular to the direction of the velocity, then it will not be able to change the direction. It will not be able to change, the magnitude of the velocity. This is really a very important idea in the history of physics. This is really, here we said, like a motion that is going to be with constant velocity, and we can say it is kind of uniform circular motion. Remember, we did introduce this in Physics 201, and we said it is when the object is moving with constant speed. Then that speed will not change, but the object is gonna go here in a circle. Then I can say sigma F equals mv squared over r, and that F is going to be the magnetic, which is going to be QVB, and equals mv squared over r. And from that, I can find the radius, which is going to be mv over, because one of the v's is going to cancel, a q times b. I'm sorry, it seems that I'm sick today. This is the reason also why I have very short videos. I can stay longer. I will say, and this is really what is going to be the motion. And of course, I will say if the charge is negative, then the object is going to go clockwise. Instead, here what we discuss is for positive charge. Now also we can find the angular speed as v over r, and that is gonna be vq times b. I don't like to use maybe the absolute value, but we know that it is going to be constant. It's going to be taking just the magnitude. Now also, we can say that the number, these really here the important, the number that represent f equals omega divided by 2 pi, that is the number of revolutions, which is, we used to maybe call it frequency per unit time. And it is independent of the radius r of the path. We call this cyclotron frequency. Okay, and that is really important for actually accelerators where we have really objects that gonna put them, we want to accelerate them in the nuclear physics, and this is one of the things that we need to, maybe if you will go to a higher physics class, then you will know more about it. Now, if the particle has velocity components parallel to and perpendicular to the field, it's not wasn't perpendicular, then the path will not be circular and is going to be a helix. Helix means like spiral. And here we're going to say also that the speed and the kinetic energy of the object, they're going to stay the same or like constant. Here I will say we can maybe here introduce. I have space here. Let's do this here. I have space. I have here maybe a problem-solving strategy that I want to introduce here, and that is. And I will say this is here when we are going to analyze the motion of a charged particle in a magnetic field. And here we know that sigma F equals MA, and that is Newton's second law. And the net force here can be calculated as QE plus V cross B when we have both fields. Okay, then here a magnetic field and an electric field. If it's gonna be just magnetic, then you're gonna use just QV cross B. If it is gonna be both, then you are going to include both. Now, one thing here that we need to know that is ignored or it is neglected since it is too small with respect to these four forces. Most of these problems are really like circular motion problems, and I will say the strategy is going to be first to determine the target variables, and here I will say knowns plus unknown, and I will say we are going also to choose a coordinate system. And it is very helpful to express, for example, let's say B equals BXI plus BYJ plus BZK. Also for V, you're gonna say VXI plus plus VY J plus VZK, or like even for the force. Then it's this like it's very helpful. Now, number 3, if the particle is moving perpendicular to the magnetic field. Then this is uniform circular motion, and we're gonna apply the above equations on top that we did use. And if like it is including like more, let's say, complicated trajectories or more complicated problems, we might do the sigma fx equals max and sigma fy equals may and sigma fz, like it is applicable. But this is really the approach that we are going to use. Here also, near the poles of the earth, there is really there is a belt going around the earth. It is called Van Allen radiation belt. And charged particles from these belts can enter the atmosphere, producing the aurora boreals here, and some kind of effects in the atmosphere. Here, another application, which is the bubble chamber, where we use it to, to test for radioactivity. And this shows a chamber that is filled with liquid hydrogen and with a magnetic field directed into the plane of the photograph here. And the bubble tracks show that a high energy gamma ray, which does not leave a track, collided with an electron in a hydrogen atom. And actually this is very important in nuclear physics. Another application that is, and I will say you can read more about these applications. These are really very important applications in the history of physics. Also, velocity selector uses perpendicular electric and magnetic field to select particles for specific speeds from a beam, and only particles that they have in kind of a ratio that is E divided by B pass through undeflected based on the anatomy of this device. There is a very important experiment in the history of physics where we were able to find the ratio for the electronic charge E over m for an electron. Then here we were able to calculate the ratio, not one of them. And then if we know the charge, then we were able to calculate the mass. Okay, this one here is really important, which is the magnetic force on a current carrying conductor. Then now I have not only a single charge, I have too many charges that they are really moving through this conductor. And it is a straight segment here that it has a length L and a cross-sectional area A. The magnitude of the force on a single charge, if we have like just a single positive charge, is going to be QV times delta B. And then if the number of charges per unit volume is N, okay, remember N, it is N over V, and V here is the volume, then the total force on all the charges is going to be NA times L, because AL is the volume. And from that, we will be able to find that the force is going to be N times Q times V times D times A. And this is LB. And then this is going to be, this one, if you remember, is going to be I. And this is LB. Then this is really how we are going to determine what is really the force on a wire that is carrying a current. Also, the force is always perpendicular to both the conductor and the field, with the direction determined by the same rule, which is the right hand rule used for a moving positive charge. And then here you are going to have the force is on that wire is going to be having a magnitude of IL times B perpendicular, which means IL be sine phi or sine theta, and the direction is going to be determined by the right hand rule. We have here L, the direction of L, which is the same direction of I, and we have B, the direction of B here. And then we can, of course, like find, this is just to find the sine of the angle. And I will say, if we were gonna make, our fingers curl, then in the direction from L to B or from I to B, the force is gonna be the thumb. And the force here, we can represent it as a vector, as cross product, I times L times B. L, it's the vector length of segment that points in the current direction. And I, of course, is the current, and B is the magnetic field. Okay, now there are occasions where we are going to have a current loop, and then here we're gonna have the direction of I will say the forces is gonna be different on different segments, and therefore we might create a torque. Then the net force, on this here on a current loop in a uniform magnetic field is going to be zero, because the forces, like on the left and the right, one of them is maybe into the page, the other one out of the page, they're gonna cancel, and also the same for the others. But the torques, we're gonna have torques here. We can define also something called magnetic moment, mu, with the magnitude that is I times A, and the direction is gonna be as in shown in the figure. Again, this is like more than one time was mentioned that the direction of A is gonna be out of the the area, perpendicular to the area. The net torque on the loop is given by the vector product, which is mu cross product with B. Okay, and that is, we can calculate the torque. Here, what if we don't have like a uniform field? Then the magnetic dipole is gonna be experiencing the following. We have here a current loop that is having magnetic moment pointing to the left. And it is in a magnetic field that decreases in magnitude to the right. You can see that it is decreasing because the lines are divergent. When these forces are summed to find the net force on the loop, the radial components cancel, so that the net force is to the right always from the magnet. Here you can see that these up and down, but these ones here, they're gonna be to the right. Now, what's the difference between a magnet and a magnet and if we have another material that is not a magnet? For unmagnetized piece of iron, only a few representative atoms moments are shown, that they are really pointing in different directions. They are really random in their direction. Now, when we have magnetized piece of iron, we're gonna find that the net magnetic moment of the bar magnet points from its south pole to its north, and then they're gonna be aligned. They are going to be in the same direction. Also, we can understand how magnets are working. We have a bar magnet here, attracts a nail that is not actually, it's not a magnet. And the magnetic field on the bar magnet gives rise to a net magnetic moment in the nail. And because the field of the bar magnet is not uniform, this magnetic dipole is attracted toward the magnet. One of the most also important, applications of, magnetism and magnetic forces is the direct current motor, where we can use this motor to rotate anything about an axis. And of course, this is just a loop that has a current going through it, and there is a uniform magnetic field here. And then when the current is flowing in the and then we're gonna have a force, and the forces, they're gonna be in directions that they're gonna create a torque that is gonna make it rotate. Then the magnetic torque here causes the rotor to spin counterclockwise. Now, also another experiment in physics which is very important, it is called the Hall effect. And that one, when we have a current that is placed in a magnetic field, we're gonna have what is called Hall EMF. EMF, remember, electromotive forces, reveals whether the charge carriers are negatives or positives. And I will say this is one of the most important and famous experiments in physics, where is gonna show us where we're gonna have a higher potential, and therefore we will be able to determine the type of the the sign of the carrier or the particle. I'm gonna stop here, and another video for the problem solving.